We have a cricket ball and it's got a mass and it's traveling at a certain speed. Luckily, they've done the conversion from kilometers per hour to meters per second for us, but you might have had to have done that. And if we can just remember how to do that, we would have said 72 kilometers per 1 hour is the equivalent of 72,000 meters per 3,600 seconds, and you land up with 20 meters per second. So anyway, that cricket ball has been hit back in the opposite direction along the same straight line with a speed of 15 meters per second. What is the impulse? Remember what impulse is? Impulse is force times time. So therefore we don't have a force. It's also equal to the change in momentum, which is final momentum minus initial momentum. So I'm going to say 0.25, it's in kilograms already, multiplied by final velocity minus initial velocity. Final velocity is 20, and the initial velocity is in the opposite direction, so it is minus 20. And that turns out to be 8,75 Newton seconds or kilogram meters per second either way. And it is in the reverse, sorry, not newtons per second, just Newton seconds. And it is in the reverse direction. How do I know that? Because what I've landed up with is I have landed up with a positive answer. Now, positive was the 15, and 15 was going backwards. So the ball came in, hit the bat, and then went back out. If I use colors, that was in, and the pink is going out. Assuming that the ball was in contact with the bat for 0.02 seconds, calculate the magnitude of the force. Well, now we know what the impulse is, and so we can work out the force, and we can say force times 0.02 is equal to 8,75, and therefore the force itself is going to be 437,5 newtons in the reverse direction. We've got a boy of mass 40 kilograms moving on his skateboard at a certain speed, as in the sketch. So he's going towards the right. He catches a bag of flour that's going towards the left. Determine the velocity of the boy after catching the bag of flour. So we are going to say momentum before is equal to momentum after. And I take the two things before, and I have got 40 times by 3 plus 5 times by negative 6. In other words, going to the left, I'm going to make negative, is equal to their combined mass, which is now going to be 45 multiplied by some or other velocity. And what I land up getting there is I'm going to get that velocity turns out to be 2 meters per second. And it is going to have a positive answer, which means it is to the right. Why? Because at the beginning I made the right positive and the left negative. We've got a man who wants to shoot a bullet into a block of wood, and we've seen one very similar to this, but they come up over and over again in exams, so we better get a little bit good at them. So let's see what happens. We've got the blocks swinging up. We need to consider that this is going to be conservation of energy. The collision will be conservation of momentum. I've got more information about the second half of the journey than the first half of the journey, so I am going to say that EP at the top is equal to EK at the bottom, and that is going to be equal to, surely it's not 800 it's 800 millimeters. Sorry, the picture's been chopped a little bit. So you've got 0.8 meters, and M is, we've put these two things together, so it's going to be 5 kilograms, because I had to change the 20 kilograms into 0.02 kilograms, and I have got a height, sorry, that's mg is 9.8, and my kinetic energy at the bottom is going to be m again, and a half mv squared. So let's work that out. I can make my life easier by just cancelling out those masses over there. And when I rearrange things, I get 3,96 meters per second. Sorry, that's not v squared, that's just v. And then I now take that as the velocity after the collision. So I can say momentum before is equal to momentum after. And I land up with, before I have got 0.02 kilograms going at some or other velocity. The block is standing still. Afterwards, the two of them are together, and they are going at 3,96 kilograms, and therefore my initial velocity comes out to be 989,95 meters per second. We now have a stone of mass 0.5 kilograms. It's thrown up with an initial velocity of 15 meters per second from a platform 16 meters above the ground. This is starting to sound like vertical projectile motion, probably is. Calculate the following. How far above the ground does the stone rise? So I'm just simply going to use equations of motion here. I'm going to say v squared is equal to u squared plus 2as. And so let's substitute. We've got a final velocity of 0. We've got an initial velocity of 15. So we're on this platform, by the way, and we're going to see how far up here it goes and how far down there it goes, and then it comes. So I'm just looking at that distance over there. So I've got 15. I'm going to square that, plus 2, and downwards is 9,8 on S. And the distance turns out to be 11,48 meters. And therefore, how far above the ground is it? I need to add this extra 60 meters of the platform. So total distance above the ground is 60 plus 11,48, and that is going to be 71,48 meters above the ground. Then they say the kinetic energy with which the stone strikes the ground. So let's see what information we can get. The first thing is that the kinetic energy is equal to the potential energy at the top of the entire journey is equal to the kinetic energy at the bottom of the entire journey. So if I go EP is equal to mgh, I am going to say that it is the mass of this object, which is 0,5, times by 9,8, times by the entire height at the top of the journey. And I land up with 350 joules, 350,25 joules. Now the important thing here is that that is the potential energy at the top, but that is equal to, mechanical energy is conserved, so it is equal to the kinetic energy at the bottom. We've got a rocket now being launched vertically upwards. It releases 24 kilograms of exhaust gas each second at a velocity of 1,000 meters per second. After 10 seconds, the fuel is finished. Ignore any loss of mass and take the total mass of the rocket at a constant 400 kilograms. So this looks like it's going to include some equations of motion and some Newton's laws. So let's take a look and see what we get. Firstly, calculate the momentum of the gas ejected every second. Well, momentum is equal to mass times velocity, which is equal to 24 times by 1,000. There's 24 kilograms going out at 1,000 meters per second, so you get 24,000 kilogram meters per second. And where is it going? From the rocket it's coming out, it's downwards. Calculate the resultant upward force experienced by the rocket. Newton's third law tells me that the downward force is going to be equal to the upward force. So I'm going to say change in momentum, Ft is equal to change in momentum. The gas was stationary to start with, and then the final momentum would have been 24,000 minus 0, force, and the time, this all happens in 1 second. So my force, by some coincidence, turns out to be 24,000 newtons. You can't just take kilogram meters per second and turn it into newtons. You need to show me these pieces of information that make that conversion. So that would be the downward force of the rocket's gas, and therefore the upward force is also equal to 24,000 newtons. Calculate the velocity of the rocket after 10 seconds. So we can work out an acceleration now. Acceleration is equal to force divided by mass, because F is equal to ma. Sorry, that's a line. And therefore we can say the force that I've got, 24,000, divided by the mass of the rocket, and I land up with, it's 60 meters per second. Sorry, why is that moving? 60 meters per second. And now if I put that in, v equals u plus at, my initial velocity was 0, my acceleration is 60, and my time is 10, so I land up with 600 meters per second. Then how many seconds have expired before the rocket reaches its maximum height? So we needed to eventually stop altogether. Now the gas has run out, so there's no further force, so the only force acting is gravitational acceleration. So final velocity is equal to initial plus at. My final velocity is 0, because now we're going to the top of the projectile. You need to understand what is happening here. We've got this rocket, and it goes up, accelerates up. Then the fuel runs out. Then it does a projectile and comes all the way back down. So from here, there's no external force at all, but we do know that at that point, it is going at 600 meters per second. So I substitute in the 600. And I have got a time, at least an acceleration of negative 9,8, and then a time. And that time turns out to be equal to 61,22 seconds. So what was the total time that it was in the air? It's going to be plus the 10, because remember, it first blasted for 10 seconds, plus the 61,22, and I land up with 71,22 seconds. Then determine the maximum height reached by the rocket. Now we are looking at the fact that it got propelled first, and then it went into normal free fall. So we need to do two different portions of this journey. And the first one is from 0 to 10 seconds. We've got an acceleration of 10 meters per, at least of 60 meters per second squared upwards. So S is equal to ut plus a half at squared, which is equal to, it starts at 0 plus a half of 60, and it goes up for 10 seconds squared, and that turns out to be 3,000 meters. The second part of the journey is from 10 seconds on to 70 seconds, those last 60 seconds that we've worked out. Well, it's not 60, it's 61,22. We'll put that into the equation. V squared equals U squared plus 2AS. Now we're under the effect of just gravity. So my final velocity at the end is 0. My initial velocity I had calculated quite a lot earlier to be 600. And we're going to square that. Plus 2 times negative 9,8, because we're slowing down, and we work out that distance over there for the rest of the journey. It doesn't matter how long it took, because we're not going to use time. And so you land up with 18,367 meters, and then you're going to add those two together with the 3, and therefore the total distance is going to be equal to 18,367 plus 3,000, and that becomes 21,367 meters going up in the air. Last one, we've got 2 trolleys over here, and they have masses. They're going to separate. They're connected by a light string. We don't know how long that is. They rest. A force of 6 newtons is applied to the 2 kilogram trolley for 5 seconds, and you need to calculate the acceleration of the two masses. So they're going off together. It's really not very tricky. F is equal to ma, and therefore it's 6 is equal to their combined mass is 5, and acceleration turns out to be 1,2 meters per second squared to the right. What is the tension in the string? The tension in the string is, remember that the 3 kilogram will be pulling backwards on that string, so we can just say that F is equal to MA. The 3 kilogram is accelerating at 1, 2, and therefore the tension in the string must be equal to 3,6 newtons to the right. What is the change in momentum of the system after those 5 seconds? Change in momentum is equal to force times time. The force that has been exerted is given here, so it's 6 newtons for 5 seconds, and I land up with 30 kilogram meters per second. And again, I need a direction because it is a change in momentum to the right. And then after 5 seconds, the force is removed and the connecting string is burnt. So the two masses move independently. What will happen to the distance between x? Will x increase, decrease, or remain the same? Give a reason for your answer and explain why. Well, because of Newton's first law of motion, if there are no frictional forces, that distance x will stay exactly the same, because these two will both continue moving at exactly the same constant velocity in the absence of any unbalanced force.